Hi there. Uh, my name is Al, and if you don't know where you are or how you landed here, this here is the first video in a playlist about group theory. Um, I have a playlist on my channel concerning geometry, Euclid's geometry, and that I was looking at for the purpose of uh, showing what an axiomatic system is and how to work with axioms in theorems and proofs. And I thought that geometry is a great example, and another good example, a very simple example of an axiomatic system is a group, something called a group. And in this video, I'm just going to give the definition of a group, its axioms, and what a group consists of. And I've written it out already, so it's just really a matter of me reading this out loud. Okay, so now I want you to close your mind and imagine, get rid of the lines and triangles and pies and all those various things, and try to imagine any kind of collection of any kind of object that you've ever heard of in your life. Okay, that's as vague as your mindset should be. Okay, we're not talking about any specific type of thing. It doesn't have to be quantities. It doesn't have to be numbers. Just anything. All right. So now I'm going to give you the definition of a group, and keep in mind that anything is possible. Anything could be, I don't know, rain showers or something. I don't know, bubble baths. Doesn't matter. Okay, now so here's the definition. The beginning of the definition. A group is a logical construct, I've said, analogous to the notion of set. So if you understand the notion of a set, which is just a collection of any type of thing, a group is very much similar to a set. Okay? In fact, it's a set plus something else. A group consists of a collection of elements called members, okay, the members of the group, and the number of which may be finite. You might have 5 or 6 elements, or not finite. You might have infinitely many elements. I think that covers pretty much all possible cases. And now what defines a group, besides the set property, is besides the set, the elements or whatever, a group is characterized, or the way I worded it here, I'll just say it in other words, a group is characterized by its elements and something called a binary operation. Okay, I've written it down here this way. What defines a group besides its elements is a characteristic binary operation that associates, together with each pair of its elements, okay, so all possible pairs, even if a group has one element, you can imagine that pairing that single element up with itself. So this is not a restriction. This does not put a lower limit on the well. A group must contain at least one element because we can't form a pair of elements. We need at least one, and we can imagine pairing the same element up with itself. That's possible. So together with each pair of its elements, either one, possibly, or two members in the same set in the manner I'm about to describe. Okay, so we have some objects and we have a thing called a binary operation. Binary operations are things that require two inputs and might produce one output, or in this case, one or two. The outputs are members of the same set. Suppose our group, I've labeled it gamma, is a set consisting of elements A, B, C, and so on. Now, those are just labels. It doesn't tell you what they are. Could be anything. Together with its binary operation, which I've given that fancy capital L character. Usually these are the symbols that are used, or something similar to this. Then we may define this operation for a pair of elements, A and B. I could have written. Even that should probably be small letters. Okay. A result, by definition, given by this expression, which is an element of the same set, gamma. All right. Well, that's all. Now you could exhaustively go through every single pair that you can think of and assign to each pair an answer to this question: what is L of AB? If you had, suppose you had two numbers, if you were using numbers, 3 and 6, and that's your group consists of those two numbers, you might say 3, 6 equals 3. And you might say 3, 3 equals 6. See what I'm saying? And I might say 6, 3 equals 6, and 3, 3 equals 3, and I think I've covered all. There are only four possible combinations of the two different objects, right? And I've assigned them for each pair a single element from the same pair of numbers, and that would be a definition of an operation. Okay? So now we have a definition of a group and its operation. So now I can write down the first of, actually the most basic definition of a group requires 4 axioms, and I'm going to list them. This is the first one. Sometimes this one's not written as an axiom, it's just a property or a requirement, but it's the same thing. A group, gamma, together with operation L and members A, B, C, etc., is closed under its operator L. And that has this meaning, that this side has to be an element of the group. I couldn't have said in my example, 3, 6 equals 7 because 7 was not an element of my group. My group has only 3 and 6 as members. So that would not be a group. Well, my thing might not be a group either, but for other reasons. But if it's not closed, it's not a group, and that's one property. Okay, so now I just wanted to make clear here, and it should be fairly clear from the way I've defined it, that I've not given any requirement that the operator L here be commutative. That means that I can commute the letters and get the same result. So generally speaking, this is not equal to this unless otherwise stated. And this I mentioned before. It's not often anyway. The axiom 1 is not characterized as an axiom, but as a requirement. But that doesn't matter because that's all an axiom is. It's a requirement. Now the remaining 3 axioms are, as I've said here, better read and written if I change the notation slightly. So I'm going to change this form of writing the operator when operating on A and B to this form. I could put it I don't want to put an underline. I could maybe put quotes or something. I don't like to think that the underline is required. Something like this. A star B. Okay? And the symbol star is called the group's operator. And there's only one. Now this, either way you write it, this here, A star B, is called the product of A and B. Okay? And the product is usually not given a letter like the one I had, PAB, which is completely unambiguous. You can see that this symbol, if I interchange the letters, I get a different symbol, so that implies that they're not necessarily the same. Unfortunately, the standard notation is to just write any old letter C, and one is to understand that this expression, which is equivalent to this one, is one where A and B cannot A and B cannot generally be interchanged. Okay, and as I just mentioned that here. Generally speaking, or in general, really, A star B is not equal to B star A. And it's just a notation that can fool a person because this looks like multiply, or sometimes they use a plus sign, this symbol, the cursor, in the place of this, and in that case as well. Unless you know something else, you can't take it for given that these are interchangeable. Alright, so now I'm going to just tell you these next 3 axioms. The first, as you might guess, the most important axiom of all, and listed first, and should be listed first, because without it all you have is a piece of junk, the associative axiom. Okay, now associativity or associative property, whatever, is not a given feature either for a set, let's say, of numbers. And I'll give you an example of a non-associative operator. Okay, subtraction is not associative, right? Subtraction. I mean, if there were something called subtraction, which we don't really have anymore, because you can write subtraction in terms of addition. But subtraction as an operator on its own is not associative. A minus B minus C is not the same as A minus B minus C. Example 5, I call it subtract 3 subtract 4. Now, is that equal to I'll just move the brackets. Put it in a different color. What do we get on this side? Well, 3 minus this bracket thing tells you that you have to work this part out first before going on. 3 minus 4 is minus 1, okay? And 5 minus 1 is 5 plus 1, which would give 6. So this side is 6. And here, 5 minus 3 is 2. And if we subtract 4 from that, we get minus 2. So we get 6. Right? This side gives 6, this side gives negative 2. So subtraction is not associative. And so therefore subtraction is not a valid operator for a group. Okay? You cannot use subtraction as a group's operator because it doesn't agree with axiom 2. Okay, next axiom. In a group, gamma, I call it gamma. Notice here that I started with S being a set of things, and combined S with an operator, and that combination results in a group. Okay, and then I have elements in my group. And the elements need to satisfy this principle, this movement of brackets principle, the associative principle, in order for the gamma to be a group. Now here I'm just starting with gamma. So if we have a gamma, a group, then the next requirement is that there exists, I should say, within gamma, at least one element in the group. Okay, so this will be explicit. Put more space here. I want to get this element thing. Ooh. One I and one I. Yeah, we have the gamma. Go on. Okay. Fix. Okay, so in gamma, there exists at least one element, I, which is in the group, satisfying A times I is equal to A for all elements A in the group. Okay? Now I believe that I here is called a right identity. Okay? You can have a right identity or a left identity, and I believe that this is called a right identity because it's on the right of the A. But it could equally be a left identity because A is to the left of I, so I don't know for sure. But one way or the other, and whatever it's named, the idea is clear enough. For any A in the group, this special element, there's at least one special element that has this property, that A times, or whatever, the product of A with I on the right gives you A back. Alright? So that's now there's just one more axiom. Well, 3 must be satisfied, so this first part is really not necessary, but anyway, there is an element I satisfying axiom 3 such that for every A in the group, there exists another element, I should say, but I've given it a different letter, so it doesn't have to be this one, or it doesn't have to be this one, such that XA is equal to 5. Okay, now the X in this expression is appearing on the left, whereas the I is appearing on the right. Let me make sure that these need to be defined in a special, consistent way. And let me just make sure that I haven't written something backwards. Okay, sorry, I did have that backwards. The X here is actually also missing a star. There we go. Okay, so everything well defined. It does turn out that we eventually we can drop the star and just it'll be implicit, right? Like you do with multiplication. If you write two things one beside another, and there are only two things, and there's only one operator in the world, so it's not that unambiguous to say AX is the same as A star X. Alright, now that's it for this bit. And on purpose, I don't want to give an example or go on any further because I'm giving you, whoever watches this, I'm going to want to give you a chance to think about these 4 requirements for a group and try to come up with an example of a group that you know of. Okay, it doesn't have to be numbers, it could be anything. Can you think of an example of a group that isn't numbers? Okay, that's an example. That's a tricky one. And can you think of an example of something that uses numbers and things like plus or time, but that isn't a group, that might satisfy 3 out of 4 of these, let's say? Can you think of a set of numbers that satisfies everything except this one? Now, I have to mention as well that there's nothing contradictory in any of this, and that there are examples of groups. I'll show you next time a few. Maybe I should tell you, maybe you can think about how to prove it. The set of positive rational numbers and multiplication is a group. Okay? No addition, just multiplication. Positive rational numbers. That's a group. Satisfies all 4 of these properties. So that's something that you can try to prove. All you got to do is show that all 4 of these rules are satisfied for every single element of the set, and that the set is closed. Well, that's the first one. Closed. Associative is true. This I thing exists and has there's at least one thing that has this property against any other element of the group, and that this inverse thing is satisfied. Every element of the rational numbers, positive rational numbers, has an inverse under the binary operation multiplication, which is the one I just gave. And you can ask yourself, is that same set of numbers that I just gave, is it a group under addition? Okay. All right. So that's it for that. And next time I'm going to give you lots of examples and prove some interesting results just with this. This is the most basic example of I think, of a mathematical construct that you can come up with. Only 4 axioms, very simple, and yet just with these 4 axioms you can prove a lot of things. Okay, and we'll get to that. All right, so I'll see you in the next one, where I'll go over some examples and some theorems to do with these axioms. See ya.